value. The value half-life is often very short, very, very complex interdependencies, and I think standard classical communication methods, classical analytics, typically are not sufficient to actually really harvest the value. So here's a little bit more detail. More than 90% of the data really never was used. A huge amount of data loses the value after milliseconds. And even though we're looking forward to 5G, the growth of data is much, much faster than actually our ability to communicate them, and which means we actually will have to be able to evaluate and utilize the data at the edge. And it actually turns out that we already have a lot of capability at the edge, because a couple of years ago already, the capacity, both storage and computation in smartphones, exceeded the capacity of all of the computers and computing centers in the world. So we have to look for that kind of a world to actually work. We're looking at AI as the next great revolution to actually work on this. So we're dividing this into 3 classes. So narrow AI is typically what you work on a single, on a single data stream, let's say audio or video or image. That is, for instance, if you sort of organize your photos with Google Photo, that would be one case. In other cases, we do things like inspection of manufacturing via video. We analyze problems in manufacturing via acoustics. And in other cases, we actually already can analyze medical images. That is, there's actually computers that can pass the US radiology exam. At the other end, general AI, this is when people expect the singularities. This is really the wild and woolly stuff, if you believe, let's say, Stephen Hawking, or the guy running Tesla that has this doom and gloom. Frankly, I'm not really too concerned about it. The real challenge that we're talking about now is what I'm talking about in the middle. Broad AI, that is where you have more than a single data stream, and where you not only look at deep insights, but where you actually look at very specific insights, where you look at what can I do in a specific situation, how can I act. This is what people do well, and I think this is where, with a little bit of work, we can actually make substantial advances. So this is just a couple of examples of narrow AI. So for instance, we got face recognition, and using that, we can actually analyze, for instance, place, in this case in basketball. Also, for instance, in sports leagues, we're already using AI to analyze, their games. Then there is speech translation, transcription. In fact, some of the things that we're starting to do now is analyze videos of entire games and then summarize those games. So that must actually mean, and then do captions. That means we actually have to understand what the action in, let's say, 1.5 hours worth of game flow, find out which are the interesting pieces, and then summarize to a 5-minute summary. So those are all things that we can do, and this is really what we're talking about when we're saying narrow AI. Okay. In order to proceed, there are 3 kinds of actions that we really need to get along with. The first one is advancing AI. This is what I would characterize as science. This is getting better algorithms, getting deeper algorithms, understanding large number of data streams, analyzing them together. So this is pure science. This is understanding. The second part, scaling AI, is what I would call engineering. So this is how can we make do with smaller amounts of data, because today it actually requires a lot of data to properly train AI models, to train neural network models. So then how do we do it more quickly? How can we do it at the edge? How can we do it with a lot less resource? And the third component, the third dimension, is trusting AI. That is, this is actually the human factor, the human control. That is, for instance, today, at least in the United States, people use algorithms, for instance, to propose penalties for people that have been found guilty in court. So how can we be sure that those penalties are not in any way biased? So ultimately what we will have to do here is make AI auditable. That is, you need to understand why an algorithm came to the conclusions that it did come, and then have enough analysis to really make sure that we remove the bias. Obviously, those algorithms typically themselves are neutral, but the results are only as good as the data that they've been trained with, and so if you have a biased data set, you will get biased results. So this is, one example of where we hope broad AI could go. I'm spending a lot of time with household appliance manufacturers, and if you've been to the floor of CES, you see there is practically nothing that isn't connectable. And you see all kinds of great ideas how we would actually proceed. But ultimately, to make real what's happening still today is sort of the bottom left of this picture. That is, we have all of these many considerations that the cook has to consider. Who is coming to dinner? Do I have any? Do you have any allergies? Do I need to turn on my exhaust because otherwise the fire alarm, the smoke alarm will go off and drive the dog crazy? So those are all things that is the entire context has to be considered by humans. And even though we've got a lot of smart machinery, the context of the situation has to be understood by humans. Ultimately, where we would like to go is that the humans give the objective, say, okay, I like to have dinner at 7 o'clock, and it's my family, and then the system will actually move to take all of those things into account and at least do as much as is possible by automation. We're not really anywhere close to this, but we believe that if you want to make progress, this is the kind of thing that we'll actually have to do. So here are a couple of things where we need to make progress on: signal comprehension, learning, reasoning, and interaction. And so for those who have been over at the Central Hall at the convention stand of IBM, we actually had the debater there. So what we're doing here is have a computer take the role of a debater in the form of a classical debate. This is sort of a UK tradition where somebody actually poses a particular position, and then one group argues pro, and the other group argues against. And so we now got software, and this is actually something that took us about 7 years to develop. That is, the project started in 2012. That effectively does the following. It starts out really analyzing an entire stream of speech. That is, if somebody puts down a position, multiple sentences, this is a paragraph, let's say, truly understands what that person is actually saying. So this goes way beyond, simple speech record. This actually is semantic understanding what people are saying. The next step is finding in a large body of information, finding facts that relate to it. And then reason about that, reason how that would actually relate to the proposition that we're discussing. And then the final step is creating, again, maybe a paragraph or two worth of speech where with truly coherent speech, proper syntax, proper pronunciation actually operates and works that discussion. And because we're in Las Vegas, actually the first possibly not very popular proposition was, should gambling be band. It was actually a lot of fun looking at the output. Let me just, can AI be biased? I think a lot of you have seen this. We know that if you don't train systems properly, you actually get really pretty bad examples. Now this is an interesting case. We're not just dealing with rational, we're also looking actually at emotions. So what you're seeing here are actually avatars. In fact, they're images of 3D avatars that, on the one hand, from an input perspective, we analyze the emotions of people that are interacting with it, and then the output would actually what you see here. In a sense, this is as I said, these are just images of the avatars, but we actually could make them real work and project them in a 3D space as well. So those are some of the things that we actually can do to move forward. So it's not only about rational argumentation, but it's actually also about understanding emotion. Okay, so with all of those things, how the heck are we going to process all of those data? And so here we look at 3 stages. The first stage is pushing standard CMOS as hard as we can. So there's traditional, standard processors, there's GPUs. The next step is getting additional architectures, doing additional architectures, and the final step where I think we're going to go that will make a huge difference, at least in some applications, is quantum computing. Let's see, jump too quickly. So at one end of the standard CMOS technologies are very, very small computers. So we've got these computers that are approximately the size of a grain of salt. They have several hundred thousand transistors. They have unique identifiers, so they actually can start, and they're only approximately 10 cents per computer, 10 cents per grain of salt, so they can be inserted in all kinds of places, do analysis, be attached to all kinds of products. At the other end is right now the world's fastest supercomputer. It's a system called Summit. It's got 27,000 GPUs, and it's 5 to 10 times fast as the closest competitor. The important, if you look at it from an overall, so to get an idea, if you have 100,000 people in the stadium, each of them has a single laptop, you would need 20 stadiums to actually get to the power of that machine. The purpose of that right now that people are using it for is to evaluate and develop algorithms in distributed deep learning. That is making progress in the engineering part of distributed, of deep learning, of training neural networks. The next step is actually then going into additional chip technology. I don't want to go into any of the details here, but we have, advances in silicon photonics, there's carbon devices, new MRAMs, a lot of nanotechnology. So there's actually, in the physical realm, there's a lot of work going on that can help us at least logically sustain Moore's law. What I do want to talk about is the next step architectures, like brain-inspired computing, that actually clearly goes away from von Neumann architectures and looks at architectures that are more similar to our brain's collection of synapses. So one recent processor that's been built has approximately 1 million neurons, about 256 million synapses. Our brain typically uses approximately 20 watts. Now this system obviously is nowhere close as powerful as our brain, but at 70 megawatts, it actually takes substantially less power than any comparable system with a comparable power that's with the standard von Neumann architecture. And what you get here is approximately 46 giga synaptic operations. So part of the way this is being done is you see an architecture picture in the center. An important part also is to understand that once you got neural network architectures, this is actually then gets into approximate computing. That is, this is not necessarily always exact. We started out in this space with 32-bit numbers or 32-bit data. We managed to get it down without losing any of the accuracy to 16 bits. Obviously, that helps a lot with the power. That is, you can either push more data through, or you have a lot less space on silicon. And there's actually now work done that we're getting close to that precision already with 8 bits. So this gives you an idea that actually with this architecture, there's huge progress that is still possible to get moving to make progress. So ultimately, this is what we'd like to get. A chip that can listen, that can feel, that can taste, that can smell, that can see, speak. Obviously, this is somewhat of an ideal goal. We're not there, we're not even close. But there is actually, there is actually some work going on that is starting to move that way. Our nose has actually a relatively large number of sensors, and then our brains take data from all of those sensors then to decide what kind of, what a specific smell is. And what this project does, it does the same thing. That is, it's not about using a single sensor and deriving conclusions from that sensor, but it uses a relatively large set of sensors and then uses AI from the output from all of those sensors and then trains it on the result of the smell. And you can see here, I'm not much of a chemist, so this is all pretty much of a mystery to me, all of those compounds. But those are some of the things that we actually can find out about now. So in order to do this kind of research, it is a combination of a lot of different disciplines. You start out with materials, because you need to find the sensors that actually react on those various compounds. And there is a relatively large set of sensors. Once you've got those outputs, you need to have efficient hardware to process it. And then once we've got that, we use AI to train it, then to decide what a particular, smell is. This actually, at least in the lab, is working very well. And so at this point, this is an example of what we can do with broad AI. And the same thing that is actually in this case done at a different lab, something comparable with taste. Now, if you look at all of those things that they're looking at the bottom, fuel, solvents, etc., I wouldn't want to get my tongue anywhere so close to that. They call it, hypertaste, but this is really very different. But again, what you're seeing here is the sensor package is going to be important. Then you've got a learning. In this case, a lot of the processing is actually happening at the edge. You've got a cloud service, and from there, then you go to the visualization. That is, what is it? And what you see here at the bottom are actually all decisions that the system already can make. That is, this is what they found out. Obviously, this is lab research. That is, we're not at the point yet where we actually can commercialize that. But this is where things are going, and there are a lot of people working on this kind of on these kinds of technologies. And those are the ones that we need to get to for for broad AI. The final point then is, okay, how are we going to get into quantum computing? This is actually probably 5 6 years away from commercial use. However, as a scientist, I can tell you from my own perspective, it's one of the most exciting developments. Way back when I started in computers, it was first explained to me with tubes, slightly different ones than you mentioned there, but effectively it was explained with tubes, and then I got to the point where at some point actually I worked with real magnetic core memory, so they were actually cubes. There were cubes with 3 dimensions of wires, and they were cooled by oil. And when you had a lot of memory errors, you actually had to twist the drive voltage to reduce the errors. So we're very much at the beginning of this, but there is a huge promise what it can actually achieve. It's not really about standard bits. That is, in quantum computers, bits can not only take positions of 0 and 1, but pretty much any value in between. For people who are sort of into linear algebra, actually it gets into complex linear algebra. That is the best way to actually start thinking about the computation, if you don't worry about the physics for now, is complex matrix manipulation. For instance, Hamiltonian matrices are actually particularly suited to be solved by quantum computers. And there are 3 dimensions that actually determine the power. A lot of people are looking just at the number of qubits. While that is one dimension that's important, the next dimension that's important is called the entanglement. That is how these qubits are combined, they're connected with each other. So typically then you cannot change one qubit without changing one that's entangled at the same time. So the amount of entanglement actually is also determines the power. And the final point, and this is very, very much an engineering problem right now, is the accuracy, the loss. That is, how long can we actually sustain a particular quantum state? So this is where a lot of engineering still has to happen before we actually can roll these systems out commercially. Once we can do that, they actually can solve a lot of problems that so far have been totally unsolvable. Now we have to understand there is actually mathematical proof that they cannot solve all NP hard problems. However, they can actually solve, in this case, easy problems and then quantum possible. The first one that we're looking at is cryptography. That is, one particularly well-suited algorithm for quantum computers is factorization. So a lot of current encryption is actually based on factorization. And so one of the things that we're telling people today is actually, if you have to think about archiving your data, maybe 10 years from now, you still need your data 10 years from now. At that point, using current encryption methods may actually be breakable. So what do? Well, there is a lot of research going on, and today you already know that there are algorithms that actually cannot be broken by quantum computers. Lattice encryption, for instance, is one of those. Another big area where we see a lot of promise is material science, that is simply molecular simulation. That is the number of states that need to be explored, and that is incredibly large. And so what quantum computers typically do is, for a moderate amount of data, explore a very, very large number of opportunities. So for instance, if you think about the traveling salesman's program, where that essentially the complexity really blows up with the number of places that need to be visited, this is the kind of solution that can be done, that can actually be made. So finally, one of the things that we're doing to help everybody get involved with this, there's a quantum network, where if you subscribe to that, you can actually submit algorithms, and try it out. For free access, there is a 14 qubit computer, and then in the sort of more commercial access part, we've got a 20 qubit computer that people can use, and in our lab we're using actually one that we're not actually able to expose right now that is 50 qubits. So this is, in summary, I think with those three steps, pushing CMOS as hard as we can, going to new architectures, in particular neural network architectures, brain-inspired computing, and ultimately quantum computing. We feel we're going to be able to fulfill the promise of AI and to deal with all of those data that all of the sensors are producing. So I want to stop here with the prepared content, but if there's any questions, I'd be happy to answer.
Questions, please? Questions, anyone?
I guess Elisa was totally clear or totally confusing.
It was totally interesting. Really kind of pushes your limits of your imagination. What is the key technical challenge, if there is one, to get operational quantum computing? I know that the physics supports it, and I know there have been individual qubits kind of demonstrating that. What is the issue that really needs to be solved, that people are working hard on?
I mean, for instance, if you look today at the various kinds of quantum computers people are experimenting with, there isn't even an agreement yet on what the physics are. That is, at IBM we're using Joseph and Johnson. Other people using, I think, electron spin and other kinds of physics that is already the underlying physics isn't necessarily clear. But one of the huge challenges there is for how long can you sustain a particular quantum state that is, as in digital circuitry, once you essentially, it's not like if you go through a couple of gates, your signal is still okay. But if you go through a couple of quantum gates, the signal decays pretty quickly. And so at the physical point, there is a huge problem with the physical engineering part to sustain the state. And then at the algorithm state, there is also a lot of open questions, because it's not like you're just gonna use Python or your standard programming language. That is how I don't buy into it simply because it's a very long and complicated question what computing actually means in a quantum state. I want to give you just one example that one of our physicists, so this was a person who's at the edge between the physics and the algorithm, physics and the math. He said, okay, look, factorization. Think about that the number that you're looking to factor is a wave, and then the numbers that you try out, whether the R factors are also waves. Let them run against each other, and where you get totally destructive, interference, you actually got a factor. Okay, and that gives you one example of how with one operation you could actually factor, try out a huge number of factors, which with standard standard von Neumann architecture wouldn't come even close. But it also is sort of and as I said, this is just an example that this guy told me. So as far as the actual math goes, I don't claim I'm really into detail, but that gives you an idea that computation in a quantum computer is substantially different from what we know. Okay, you've got registers and you've got your data going in and you've got your adds and subtracts and all of that. That is your standard digital circuitry.
Is Joseph Junction cryogenic?
Yeah, it needs to be run in millikelvins.
Are most of the quantum technologies required?
So far, all of the ones that I know about, and I cannot guarantee that I know all of them, are all of the ones that are actually at sort of the millikelvin level. which doesn't make it easier.
Yeah, I have a question. From the hardware-software trade-off perspective, how does quantum cryptography differ from a regular cryptography?
Excuse me?
From the hardware-software trade-off perspective, how does the quantum crypto differ from non-crypto?
I don't really think we actually know enough yet. There is a large amount of research going on in quantum algorithms. But to tell you the truth, this is not an area where I've been diving in, and I'd rather tell you I don't know than give you bad information.
Any other questions, please? Small token of appreciation for Martin.
Thank you.
So, thank you. We are adjourned for this session. We're now in the breakout period.